G'day everyone, welcome to Lubrication Experts. And today we have a very exciting guest. We have Evan Zabawski from Eurofins Test Oil. He's the Senior Technical Advisor there. Now, I've had the opportunity of seeing Evan speak a couple of times. I think it was at STLE a couple of years ago. And
Yep.
one of the few people that can make oil analysis seem entertaining. So that's one of the reasons I wanted to bring him on. Any number of stories and a huge amount of experience that he can bring to the table. So, Evan, thanks so much for joining us.
Well, thank you. Glad to be
Yeah,
here.
no, this is gonna be good. It's kind of long awaited. I've been trying to get Evan on, but schedules and whatever have never sort of lined up. So, let's just kind of like start maybe with the very very beginnings of oil analysis, and maybe we want to say the degree of maturity to which it's being used, because you and I know that there are many versions of oil analysis. And we see many different, let's say, program maturities out there. So I think maybe where we want to start is your assessment of the current state of oil analysis. So what is the kind of quote unquote average maturity level that you see among not even just your test oil customers, but even beyond that as well? Is it just a compliance exercise? Are we just ticking the box because, corporate says that we need to have an oil analysis program? Is it we're doing kind of pretty menial like traffic light analysis? Red light means change the oil kind of thing. Or do you see it, being used to its fullest extent, where we have different levels of oil analysis which are being applied based on the criticality of the asset? Maybe you're doing some exception testing and that sort of thing. And there's probably, just to preface this, there's probably not one answer. I'm sure there are different industries that are doing this better than others, maybe. What's your kind of general vibe on the state of oil analysis right now?
Well, the way I always, address this kind of topic is to actually talk about the history of oil analysis briefly. And that is that, about say 60 years ago, we had commercial labs, but not everyone recognizes that for about 20 years before that, we had the earliest incarnations of oil analysis occurring at trucking fleets, railways, military. And the thing they all benefited from was large fleets of singular make model combinations. And once commercial oil analysis labs came about, that's who they targeted, was again, similarly large fleets of few make model combinations. But where oil analysis as a technology, a strategy, whatever you want to call it, has matured is, as I joke now, we have endless make model combinations with thousands upon thousands of one-offs, where there's an end user using a piece of equipment that does not exist anywhere else in the world, utilized the same way under the same circumstances, et cetera, et cetera. And so people who have a knowledge of the history of oil analysis, people who've experienced oil analysis, they grew up in a world where oil analysis worked. And so they like it. And how it worked was, back to your terminology there, the traffic light system, where it was really red or green was kind of the way we went. And I find that there's a lot of industries out there that have not evolved past that. They are stuck to where we were, say, 50, 60 years ago, and they are not really utilizing it to their fullest extent. I do find, to your comment, that yes, a lot of people are ticking a box. They are aware of oil analysis and they may not have experience with it, but they know it's something they, quote unquote, they should do. So they do it. One of our colleagues in the industry who retired last year, he used to joke that when he first started into the industry, he was selling filing cabinets, because he said people did oil analysis, people received reports, they filed them away. And therefore, the compliance was very, very low. Back to your question, I do think there are a few industries. Mining would be the one with the most experience in my experience, that actually utilizes it to its fullest extent, that tries to truly make it predictive, actually reads a report and anticipates that by the next report, something will be off, and either requests different analysis or takes the corrective action before it gets to the traffic light being red and saying, "Oh my goodness, what'll we do?" And then frequently, what they do, like you said, is, well, change the oil, which makes the next report green, even if it didn't fix anything. So I would say that yes, it's all over the map. There are a few that are just checking a box. There are a few that are reaching a full potential and actually leveraging it in a way it was intended to be used. But I would say the dominant answer is yes, it's the traffic light. People think oil analysis is simple. They treat it as it's simple, and they use it in a simple way. So they're not really getting as much out of it as they could.
Yeah, and maybe a little side discussion on there because if it is just a compliance exercise, what is the business getting out of that? Like, is there, are we doing it for insurance reasons predominantly? Do you think we're doing it just because we've always done it? It's like
Yeah,
culturally built in. Like, what do you think is the reason that we're just kind of taking samples and sending them
yeah.
off?
There's a small amount that is regulatory or insurance related. Like I think of steel mills and utilities in particular. They fall under such regulations, but they are also people who tend to take it a bit more seriously, uh, probably because they're being forced to in some way. I would say that the most that are just ticking the boxes, yes, out of habit, right? It's kind of always done what they've been doing, and mostly I would say though it's because they think it works,
Mm,
right? They think that using the traffic light system, changing the oil when it goes red, making the next report green is actually doing something because the machine ultimately didn't fail when they got a red report.
mm,
Now, when the machine does fail, if it fails, let's be honest, not all will fail due to a lubricant related issue. But when they fail, they don't always blame oil analysis. They often find something else to blame. And they don't really fault the program. They just continue on. So that is also habit based of what I like to call lube, fail, repeat, because it's this repetition of that same activity, usually an oil change, and it doesn't really resolve anything. So, yeah, it's going to repeat itself. You will get another red report down the road. You will do the same sequence of activities. You'll change the filters, change the oil, check the breather, whatever it was. You get some green reports, and you'll just assume that the program works. And like I said, until such a time that the machine fails. And when that happens, you don't tend to think it was the program's fault. You think it was the machine's fault somehow. So,
yeah. I like that.
really,
Lube, fail, repeat. Kind of reminds me of
yeah.
what was it? Edge of Tomorrow, the Tom
Yes,
Cruise.
that's what I modeled it
Yeah, yeah.
after.
Which was,
Because
I think that was live, die, repeat is how that was marketed,
yeah,
right? Taken from the graphic novel "All You Need Is Kill."
yes,
Great graphic novel. All right, so that's kind of like the why of why some businesses might be trapped into this kind of. It's almost like a hamster wheel of oil analysis where we're kind of doing it,
hmm
um, but it's a kind of a pointless exercise, right? It's what was the Greek Sisyphus, but, pushing the rock up the hill. So
yes, exactly.
um, okay, for those people who are just doing traffic light analysis, and for people who are kind of taking it that one step further, I mean, obviously the traffic lights they have to be triggered by something, and I think this is probably
hmm
most people's intersection with, let's say, generously interpretation of oil analysis results. So, um, and I think people are often doing this blindly, and they're taking actions with no understanding of how those red lights are generated, or the yellow
Yes.
lights, or um, I have seen a couple of labs who have moved beyond traffic lights and they've gone to the emoji system. So
hmm
sad face with thumbs down. Um, okay, maybe it would be helpful to explain like where did those limits even come from? Because most people, I would say, I mean, most commercial labs these days give you the capacity to define your own limits. But let's be
hmm
honest, the vast majority of people are not defining their own limits. They're just using the prescribed ones from the lab. So where do those numbers come from?
Yeah. So there's essentially a couple of good sources of where they used to come from. One was OEMs, and another one would be the lubricant companies themselves. Then we started seeing a migration towards commercial type industries creating like user groups or whatever. So there'd be like an industry set of limits. So, like I see the model behind you, there'd be a wind turbine user group, and they would say these are the limits for all wind turbines, and they would treat them all generically equal. Where that evolved to was commercial labs eventually locking in their own, because as I always try and be honest when it comes to choosing a commercial lab, we're all held to the same ISO standard for quality of our results. We all tend to use the same ASTM and other methods for the testing. So at the end of the day, I don't try and distinguish one lab from another based on the testing, the quality of the data, the numbers, for a simple way of putting it. So how people try and differentiate themselves is on the interpretation. And as you say, we put loose air quotes around the word interpretation because it's a cursory analysis of some data. And it's held to, generally speaking, most commercial labs use their own inside, as you will, set of limits that are generated by combining either the OEM and the lube supplier limits, because the OEMs will typically supply limits for wear metals and contamination. The lube suppliers will typically supply limits for viscosity and other parameters such as additive levels, perhaps. But the industry ones, if they exist, those ones are kind of a combination of mostly the wear and contamination related ones, and to a lesser extent, the product specific limits. They might have a viscosity limit as an example because it's the recommended grade for the application, but they won't get into the nitty gritty of how much calcium, phosphorus, zinc should be there, because that may vary from one formulation to the other. So labs typically started with this. Then what I saw was an evolution whereby labs would take a crosscut of a chunk of their data. Usually they would look at the last, 100,000 or 1,000,000 samples, whatever it was. They try and make sure it spanned at least a calendar year, so it would include any seasonal variances that might exist. And they would basically do distribution curves, and there's even an ASTM standard for this. ASTM D7720 recommends using bell curve distribution, right? 2 standard deviations is where the first caution comes on, like you say, kind of a yellow light. 3 standard deviations is the red light, and you can typically assume anything within 1 standard deviation is your green light. What's happened then is, again, because like I said, if you treat that all labs are roughly the same when it comes to the numbers, and they got to be different on the interpretation, well, if everybody has similar customers, everybody's going to end up with similar limits. So where they really try and differentiate themselves, and this is a good thing, is they actually will cross-cut the data. Instead of just their entire database, a whole year or whatever it might be, they take an entire singular customer's database and just say, okay, from all your machines, here's, again, probably same thing, 1, 2, 3 standard deviation sections, and create customized user-specific limits. But at the end of the day, they are based off of past behavior and anticipation that future behavior is somewhat similar. So in a nutshell, where all these limits come from is a little bit empirical, right? It's based off of old data, old experience, and just to a lesser extent, because it only applies to some of the numbers, the standards to which everything is held to, like as an example, viscosity. Viscosity frequently has a 10% limit to it, plus or minus 10%, because that's the ISO grading system says plus or minus 10%. So nobody's going to, make that any broader than that. They might choose to tighten it if they can see empirically it's able to stay tighter than that. But on the outside, worst case scenario, they're just going to plug in plus or minus 10% to the viscosity limits and let those ride. So that's kind of where I've seen the evolution. And some people choose to adopt only the OEM limits, only the lube supplier limits, maybe both. Some people choose to create their own, like you say, or have the lab create them for them, because the lab, of course, has the same access to the data and usually the tools to do it a bit quicker. But if you just go with the generic ones, then yes, they're just a crosscut of all the lab's customers, which, depending on which lab you deal with, some have more experience in one industry than another. Some have more experience with one type of machine than another. And you may think that makes them better, but what I find is it just tends to make them broader. So more middle of the road and less specific. And that's kind of why I always encourage people. I said, no matter how a limit is created, you have to appreciate it's a static number. And being a static number, you have to ask yourself, what conditions did it take to create that number? Under how much usage, what speed, what temperature, what environment, and all these kinds of things that went into creating that number, and then say to yourself, is that how I'm operating? And of course, the short answer probably is no. There's at least one of those variables. So the common example I like to give to people is this. Just presume 3 pieces of equipment. So I go with gearboxes because that's kind of universal. Most people kind of picture what one of those looks like. And say there are 3 different sizes. One's only 20 liters sump capacity. The other one's 200, and the last one's 2,000. So multiples of 10 increase. Easy to keep track of in your head. Then I suggest to them, in the first gearbox, it only has 20 liters of oil in it. We have around 1.5 grams of metal content. What I'm saying is if we filtered out all the wear metals from the oil, accumulated into a tiny little pile, it's about 1.5 grams, about the size of a fingernail. Now, in the 200 liter gearbox, we do the same thing, filter out all the wear metals, collected into a pile, and I play with the units here, so it's not so easy to see the math behind it real quick. I say it's about a half an ounce. And then in the 2,000 liter gearbox, same thing, collect all the wear metals, and it works out to about 1/3 of a pound. So usually when I do this to a big group, an audience, I say, okay, there's your 3 gearboxes, 20, 200, 2,000 liters. We have 1.5 grams, we have half an ounce, we have 1/3 of a pound. Which one is in the worst shape? And most people seem to favor the 20 liter gearbox. And it doesn't matter which one they pick. I'm not there to judge, but I say, well, what's interesting about the math on all that is that all 3 of those work out to be 100 parts per million. So I said on an oil analysis report, they would have all looked the same. So then I say, well, what if we add something to it? What if I tell you, though, that the first gearbox, the smallest one, had 1,500 hours of service. The middle one had 1,000 hours of service, and the last one only had 500. Well, then people quickly change their answer and say, no, it was the bigger gearbox. That's the worst one. Shortest runtime, got to 100 ppm. That's the worst. And I said, well, no, let me throw one more thing at you, though. I said, what if we just make all the runtime the same? Make them all 1,000 hours, similar runtime in all 3. But now I tell you what the previous result was. In the first gearbox, it was 90 parts per million. In the second gearbox, it was 30. And in the last one, it was 80. Now, which one's the worst? Well, then everyone quickly picks the middle gearbox and says, that's the worst one. And I said, well, every time I change one variable, you change your answer. I said, do you see why a static number will not work? You cannot accurately, for all samples, consider a static limit at wherever it came from. Like I said, any of the 4 common sources of OEMs, lube suppliers, industry, or commercial labs experience, all of them are a point in time under certain conditions that may not hold true to today. And so what I tell people is, and it's a bad, pun, joke, mantra to have, but trend is your friend, right? You have to trend results to really see what's actually happening. Is it changing in a way that's good, bad? And what I always try and be clear on is this can come right down to 2 sister units, 2 units near identical at the same facility or in the same plant, similar run times, similar operating conditions, switch up the operators, whatever you want, try and make them as equal as you can. And I say one may sit at 80 parts per million consistently all day. The other one will sit at 30 parts per million consistently all day of the same measured wear metal. And I said, at that point, that's just what's normal for each of those. And so kind of back to your first question there about talking a little bit about the history of oil analysis and the complacency is one thing I always try and say to people is, look, if you think about the 4 basic condition monitoring technologies that exist, we have vibration, we have ultrasonics, we have thermography, and of course, oil analysis. So the first 3 all have known signatures, known patterns, known sort of frequencies, whatever you want to call it, that a singular reading can tell you something very telling. And what I always try and be honest about oil analysis is it lacks that. You show me one report, one moment in time on a system and say, how's this report look? I'm like, I have no idea. First question I'll say is, what was it last month? What would it look like the time before? What's the new oil look like? I need all these points of reference to be able to accurately, adapt my recommendation. And every time you add a new piece of information, just like my example to you, it may change the outcome. So to digress for a different path here for a second, there's an example report I like to show people. And basically the trend over time, what you notice is simply that it's a bearing. It's just an anti-friction bearing. You don't know how big it is, but you know it's an anti-friction bearing. So you're just picturing, okay, bearing in a housing, could be on a pump, a motor, whatever. The oil is specified as an RNO 68. You read the report, and all you notice is that the new oil does not seem like it contains any additives, because that's common for RNO products, that most of the additives that are used don't show up. They're not calcium, magnesium, phosphorus, and zinc based typically. You notice, though that is the oil that is supposed to be there, you are seeing increasing levels of calcium and phosphorus. So there's your first clue something's wrong. What you then see is the viscosity is unchanged. It is holding steady at 68. So you're like, all right, if this is the wrong product getting in there, it's obviously not affecting the viscosity. But the big thing that you notice on this report is the wear metals are terrible. And in fact, the particular example I go through has a comment on it, and it says post-failure. The sample was taken after the failure occurred. So easy part is we don't have to figure out what went wrong. We just have to figure out why did it go wrong. So when we keep reading the report, the next thing we notice is the particle count is high. So you see a high particle count, you see some silicon to back that up, and it even had an analytical ferrography done on it, and that showed high levels of dust and dirt amongst all the wear metals. Now, the way I teach people to read reports is ignore the effects, focus on the causes. So wear metals, those are all effects. That's something drove it to wear. That's not what we're here for. What's the cause? Well, the easy answer is we have calcium and phosphorus, signs of another product getting in there, and we have signs of silicon and a high particle count. So I asked people, I said, can you think of one event, one action that would make both those two sides of the equation happen simultaneously, and this is the important part, to such a point as to drive a bearing into a failure mode? And so usually what people come up with as an answer is they said, well, somebody added the wrong product, but it was the same viscosity. I'm like, all right, you're ticking off how the calcium got there, how the phosphorus got there, why the viscosity didn't change. They said, but it was added using a dirty container and or a dirty funnel. And I say, all right, that would tick off the box for how the silicon got there and why the dust and dirt is showing up on the analytical ferrography and the particle count, etc. I said, but do you really think a one-time use of a dirty funnel or a dirty container would throw a bearing into a failure mode in a matter of weeks? And of course, most people start to go, no, probably not. And I say, well, welcome to the club. I said, you've just done data interpretation with the lab's level of knowledge. So now let me become the end user and tell you two things that the end user would know the lab doesn't know. The end user knows that the particular bearing housing operates in a very dry and dusty environment, and it has seals that are frequently greased. So once I reveal that to people, you can see the little wheels start to turn there. And then I show them a slide and say, here's the grease they're using. And it's a calcium sulfonate EP grease. So now you have a source of calcium, it's the thickener. You have a source of phosphorus, it's the EP additive. It's a little bit of grease getting into the oil, so it's not going to affect the viscosity. So you've explained half of it again, but you go, why would a little bit of over-greasing getting into the oil cause the bearing to fail? And you go, well, it's not just over-greasing, allowing grease to migrate into the oil. It's that over-greasing a bearing, the seal on the bearing will blow out the seal. And since it operates in a dry, dusty environment, now the dust has gotten in because the seal is no longer functioning, and that's what led it to a failure. And of course, everyone has this big look of revelation, like, oh my goodness, yes, it was staring me right in the face. I said, yeah, but until you knew it was in a dry, dusty environment with seals on it that required greasing, you would never have come to that conclusion. So I say to people, when it comes to oil analysis, what do you think you're paying for? You're paying for the numbers, or you're paying for the interpretation? And some people say, well, that's how labs differentiate themselves, is they really are saying our interpretation is better than the other guy. So that's what I'm paying for. And I'll say, well, my opinion, you don't have to agree with me, but my opinion is you're paying for the numbers only. The analysis, the interpretation, back to your comment, it's free and it's worth every penny, right? It's a limited interpretation. And oftentimes, back to your original question, it relies on static numbers to determine what's a high iron look like, what's a high silicon look like. and has no idea about the actual circumstances of how that particular asset operates in its particular environment. And therefore, when you read it only from that lab's perspective with static limits applied to it, you're barely seeing what you can. And that's why, back to your very original question, why the traffic light system is, it's deeply flawed by today's standards. We just don't have that same gross amount of same fleet, same make model combinations where we can trust that historical empirical data will represent what the next future failure is going to look like. Now we have to accept the fact there's so many variables that in the end, the trend is your friend, right? That you look at every report individually. You don't care how it compares to its sister or its brother. You just look at each one and say, okay, what is this doing in comparison to the last few samples? And expect that, yes, certain values will increase, certain values may decrease, and that's the normal trend. The question is, are they increasing or decreasing faster than normal? Or is there a sudden change in direction that's inexplicable?
So
That's not because you topped up with fluid or changed the filters or did something else that you can account for. Again, information the end user has that the lab would never know.
So with the trend is your friend, I think that's probably getting to the idea of us looking at like rate of change limits, right? So the
Yeah.
idea that instead of, let's say, wear metals, let's, for ease's sake, let's say iron, instead of it flagging at
Mhm.
50 parts per million, we're going to flag it when the increase has been more than, let's say, 2 parts per million per 50 hours, or whatever arbitrary number we're going to come up with here, right?
Yeah.
So um, I think I've only ever seen maybe one or two OEMs prescribe rate of change limits. I think MWM gas engines comes to mind. There are a couple of others. Um, why are those not more common? Like, you would have thought, for example, if you look in the Yenbarker, I'm just bringing, because I used MWM as an
Mhm.
example. If you look in the Yenbarker handbook, for example, most of the wear metals, and as well as contaminants, silicon is just set to a hard limit for landfill gas engines of 200 parts per million. From
Yeah.
memory, was it copper? I think it was like 15 parts per million. Aluminium is about 15 as well. Iron's something like 20. These are all kind of absolute numbers, which, like you said, are not necessarily reflective of the wear rate. Um, so why aren't rate of change limits more common, especially when the OEMs presumably have a ton of data that's available to them?
I can give you a two-part answer to that one. The first part, easy answer, is why most labs don't use rate of change is because they don't always have the hour information. So they're lacking the actual number that they would need to determine the rate. Second reason, though, bigger reason, is they don't work. So a good example of this, there was a interesting, call it a study, if you will, that was published, and focused on Caterpillar 3406 engines, a fairly common engine out there in industry. And it focused, specifically on iron, and was trying to explain why rate of change didn't work. So the graph plotted the iron compared to the hours of the reported samples, and it had a distribution curve on it to show how many of those samples or how many samples drove each of the numbers. So there was a very high peak of samples taken at 250 hours and a smaller peak at 500 hours, because those would be fairly common sampling intervals. So you can see that you would have greater confidence in the values at those two key points. Now, what was interesting is that at 250 hours, the average iron content in the engines that surveyed by this lab, it was 12 parts per million. At 500, what we're all expecting me to say at the end of the sentence is it was somewhere in the neighborhood of 24, maybe even 25, but it wasn't. It was 21. And so they go, well, why at double the usage does it not have double or even slightly higher than double the amount of iron? So when you look at the graph, if you look at the y-intercept does not start at 0. It doesn't start at 0 hours having 0 iron. It starts at 0 hours having about 7 parts per million iron. And this is, a fairly common phenomenon we're all aware of, usually referred to as oil hang-up, in that when you drain the oil out of a system, you never get all the oil. So you always have residual old oil when you mix in the new oil. And this number has been quoted up to about 25% of the volume, et cetera, whatever you want to believe. But this data showed that that was in fact a pretty accurate representation, that that number is closer to 40%. So what I'm saying is, whenever you drain your oil, whatever the values were at drain, take 40% of that and consider that your zero starting point, your 0 hour starting point. So when you do rate of change, all you do is you take your number that you get, divide by the hours reported, and see what that comes out to be. Well, because of this non-zero intercept, what you actually see is a slightly weird curve to it, where the rate of change seems to be extraordinarily high in the first few hours, drops like a stone, and then levels off. But when it does in fact level off, it levels off with a slight downward slope. So as much as we think rate of change is always equal, and when it increases would be a sign of danger, the fact is it's not equal. It's actually slightly downward. So if you try and correct for all this nonsense and say, okay, let's make it work, let's force it to work. So you take that 7 ppm at 0 hours and do a baseline correction and just subtract 7 from every result and force it through a zero intercept. Well, then what you see is still a flat. Now you get a flat trend, which is good. You don't get a weird high starting point, but it still has a downward slope. So in the reality is, if we rely on rate of change, by the time the rate actually increases, it's probably gone into failure mode. So it's too late. And, some people have tried to say, well, this is because as things wear, they have less to wear. And I'm like, look, that's like using the word break in, which is an old term. Not a lot of equipment actually has to break in anymore. So this data wasn't collected on new units only. It was collected on all units in service at a bunch of different similar customers and similar applications. It was about 5 different large mines, I think, were used to compile the data. And it just showed that the fallacy of rate of change is that we presume actually, that the rate should be equal throughout its life, throughout a service life, not necessarily asset's life, but throughout the service life. And it is fact, it is not. So, like I said, even if we had the hours, which we don't always have the hours, but even if we did have the hours, we're basing it off a false assumption. So it doesn't work. And that's why most labs stay far away from rate of change, and why I think OEMs don't adopt it and all that. And so as an industry, we've recognized rate of change. It may work at an individual site, if they do it themselves and they do, force baseline corrections every time they do an oil change. But the reality is that, again, there's so many other variables kicking in that the rate of change for one unit will be different than the rate of change for a sister unit. So unless you're willing to do it individually for every one of them, you're not likely to come up with a number that says, look, we expect, like you say, 2 ppm per hour of use or something like that as the ballpark benchmark type number. We're like, no, you know what? Some units, it could be 0.2 ppm for every hour, and another one could be 3, and both of them are normal.
Yeah.
By our, every other metric we have to go by, these machines appear to be operating normally. Yeah. So yeah, it's in short, it just doesn't work.
Yeah, interesting. Interesting. Okay. So if we are a business that is kind of trapped in the hamster wheel of traffic light analysis, and we're looking to go beyond, right, to the type of, trend is your friend analysis that you've been discussing. You've talked a little bit of the mechanics of like how to do that in terms of looking back at, and incorporating operational data as well as some of the context around the asset and doing it on an individual basis. So that's kind of the how. Maybe another question to ask is, in the businesses that you've seen successfully transition and kind of, walk up the maturity ladder, who's driving the change? As in, where is that coming from? Because, people need to be incentivized to do it. And there needs to be some level of direction. There might also be a component of knowledge, whether that's, that comes from training or simply in-field experience. But who are you finding in the organization is driving, let's say, the maintenance and reliability teams to a deeper level of oil analysis interpretation?
Yeah, usually it's the middle levels of management or higher. Is not the boots on the ground person putting the oil in the machine. It's not the person who pulls the oil sample, nor is it necessarily even the person who reads the report. but who they report to, whether you want to call them the reliability leader or manager or engineer, whatever title that may be, it generally starts there or possibly even higher up. Sometimes it's a plant manager who, and I would say, guessing here, has their roots in reliability at some point in their career and knows it works. So therefore, it is kind of a top-down, motivation to do this, and it's kind of where it has to be. I've always argued that if the upper levels of management aren't supporting it, the program's generally doomed to fail. And back to our comments earlier, about complacency, some of the most complacent people, most habit-based people, don't want to use the word complacent as meaning like lazy or uncaring, but just habit-driven people are the ones who have to do more tasks frequently. So it is the boots on the ground people, because they do the same kinds of things day in, day out, week in, week out. Whereas the higher up the ladder you go, the less frequently they repeat some of the exact same tasks. So they tend to be a bit more willing to assess a situation without going, well, let's just do it the way we did it last time, right? They tend to be a bit more fresher about the whole thing and say, well, how can we approach it this time? They're also in the authority position, to affect a change, right? People who are at the bottom of that ladder, as well-intentioned as they may be, as trained as they may be, and as motivated as they may be, they can be very ineffectual if they don't have that support from somewhere higher up the ladder. So where I've seen it successful, it has definitely been at least the bosses of the people who are on the floor or higher that has to say, we're doing this. Once they say we're doing this, generally they do have to, convince the people lower down on that ladder that this is a good idea and we're going to do it. And they sometimes have to justify or convince, whichever way you want to say it, the people higher up the ladder that this is how we're going to be spending our money, or why I'm hiring more people, or whatever it is that we're doing. Because usually there is an incurred cost to doing the program better, because it probably means, one, you're taking more samples more frequently, and two, you're spending more time interpreting, reading, disseminating the information somehow. So that means more work orders are created with more things to do than just simply the loop, fail, repeat, where they just go, well, I'll just change the oil and we'll be done with it, right? The next report will be fine. Like, no, let's go inspect the breathers, come back and tell me what you saw. So somebody inspects the breathers, they come back and say, oh yeah, the breather was damaged. They go, well, we should change that breather. They change the breather and they say, now let's resample it, right? We don't resample it the next day. That's not enough time. We need to resample it the normal interval. But when they resample it the normal interval, they're remembering, they go, yes, we changed that breather. It seemed like it was a bad breather. It was damaged. So they check the next report a month later, whenever it is, and say, well, if that was the only thing wrong in the system, then we expect the results will be more or less the same. And they see the results are more or less the same. They go, we fixed it. That's what was wrong. We can carry forward knowing that there's no other issues. Whereas if it continued to increase, even though they made one change, they go, that wasn't the only thing wrong. We need to go back and look for something, right? And they close that feedback loop of, here's what the report says, and here's what the person who actually walked past that piece of equipment had to say. Because oftentimes, so many facilities, those are not the same people. Mm. The people who read reports, do the interpretation, are not the same as the people who have to, either do the inspections or do the repairs or the oil changes, whatever it comes down to. So once you have that mid-level management driving this, they tend to close that feedback loop, and those people tend to talk to each other. And that's when you start to see some success, and some success tends to drive more success, because once people see it kind of works a little bit, they're more invested to see it work a lot. And they will take better samples. They will read the reports with a bit more diligence. They will listen to the interpretation with a bit more respect, is the word I usually choose for it. They'll actually care what the person has to say and go, well, yeah, if you're telling me the report says this, I will go check that, because those two things might have something to do with each other. And like I said, it just starts to build from there. But that's usually where I see the success. Yeah. It's got to be mid-level management working with the team to convince them that it's working, right? So you got to be part salesman here. You got to, you got to sell it to people on both sides of the ladder, higher up the ladder, lower down the ladder. And usually you can sell it by, what we call in industry, the war stories, sharing the little successes we had and say, well, this one time we caught this issue, and people go, okay, well, if it can catch that, maybe it'll catch something else. And it builds, right? It's not fast. It's not immediate. It's not a switch we can just turn on and say, yeah, here, we're doing it, right? It takes time to do it, but that's where it usually, like I said, my experience has had the best success.
So that actually kind of brings me to a later question that I wanted to ask, which was we're seeing increasingly, especially among the big mining companies who, as you pointed out, maybe have a kind of a deeper level of maturity when it comes to the interpretation of oil analysis results and using oil analysis to its full extent. So obviously mining is huge over here in Australia. It's kind of, the industry, for want of a better word. Um,
Hmm.
there is a maybe a trend towards having centralized reliability as well as hydrocarbon teams. So I'll just pick one of them. Rio Tinto, as an example, has
Yeah.
a kind of a centrally located hydrocarbon management as well as a kind of a reliability team that'll be based out of Perth, and it's what you imagine like the control center looks like. Lots of big screens. They can see the
Yeah.
data feeds coming in from every single mine site that they have. Let's say, for example, in the state of Western Australia, um, and you've got, to use the term boffins in chairs, doing a certain degree of interpretation. Now, I can see, benefits as well as downsides to that. Namely, the benefits would be the sheer amount of data that's being collected in a centralized location gives you the capacity to see trends at a 30,000 foot view. My concern over doing that is that you lose the operational context that you were talking about, which is for each individual asset, to really utilize oil analysis, you need information about the individual assets. So, are you able to speak to the success or otherwise that you've seen out of adopting this kind of model?
Yeah, yeah, I definitely. I've seen what you've described. Centralizing a team somewhere, usually offsite to all locations, not even at one of their locations. And like you say, there are benefits to the big data side of it, where they can take those huge swaths and say, okay, here's an overall trend we're seeing. But like if you go back to the example I gave, being in the end user position compared to being the lab position, the lab position is, yes, the remote person doing the interpretation without knowing any contextual piece of information regarding how that asset's operated. The end user one is somebody who's actually got boots on the ground and can walk up, see, smell, touch that piece of equipment and go, okay, I can see there's all this grease pouring out of the seal. I can see all this dirt stuck all over that seal. No wonder that bearing failed. It just looks nasty, right? Whereas from the lab's perspective, what are they picturing? Well, they might be picturing that, but they also might be picturing a perfectly clean looking bearing operating the way it's intended to operate. So they make their interpretation based off of either a wrong assumption or no assumption, right? They can't assume anything, so they don't factor in the environment to it because they're like, well, it is whatever it might be. So I definitely have always tried to defend those boots on the ground people and say, look, no one will ever do a better job than somebody who walks the equipment down. Somebody who is there. It could be the operator, it could be a maintenance individual. Sometimes it could be an electrician, right? Somebody who's got nothing to do with the lubrication side of it, but because they walk around frequently and they see it, they smell it, they touch it, they know what normal is, and they know when it's not normal, right? They can walk up to you and say, "Hey, that unit over there? It burped out its dipstick. It's laying on the ground." Right? Oh, that's not right. Whereas 1,000 miles away on the other side of the country, you've got somebody looking at a bunch of data going, "Huh, this one's unit is showing higher signs of silicon than the other ones. I wonder what that's about." And really, the simple answer is, well, if you actually had laid eyes on it, you would have known what it was before the analysis even told you what it was. So I do think there's a certain loss if you only rely on the remote group. I think there's powers, there's some synergy maybe even to be gained by centralizing it, because I have seen the downfall. I have a client who is 5 coal mines, all operated geographically in a similar region, very close to each other. And when they took a view from like you say, from the 30,000 foot view, they recognized that their entire fleet of brand new bulldozers showed high signs of nickel, every last one of them. So it wasn't just one of the 5 sites, it was all 5 of them. And they were quickly able to narrow it down to it was only the ones they'd recently purchased, none of the previous ones. So long story short, that one turned out to be Caterpillar had chosen a different bearing vendor, and the new bearings were being supplied with nickel flashing on them. So, but the thing is, if each individual plant had to address why is nickel showing up in only a few of my units, they may or may not have recognized it was only the newest units that were doing it. Even if they had, they might have thought, geez, we must be treating the new ones a little rougher, or whatever it is. And they might have discounted at maybe not all 5 sites, but each one of those 5 having been responsible for their own interpretation of that high nickel on only select units wouldn't have seen that bigger picture. What that No, realistically, there was a common factor here. It was that they were all new. Like I said, that's something that you can gain from the 30,000 foot view side of it. Now, you will lose if you only, like I said, if you only do that, you will lose the boots on the ground aspect of, hey, it doesn't smell right. It's running hotter than normal. I can see oil seeping out of this, or any comments like that where you go, you know what, those are often the best comments, the ones that are truly predictive, that catch things at an earlier stage in the oil analysis, waiting to be triggered by a high contaminant count or wear count or an oil that's oxidizing or whatever it might be. So, I don't think you can say one has to or should replace the other. I'm not saying we should only go to boots on the ground people, nor am I saying we should definitely outsource everything to a team of very professional, highly educated, people who sit in armchairs, far, far away. Each has their benefits. But back to my comment I made on the previous question, it's kind of like I said, it's a feedback loop. It's really successful when they talk to each other.
Yep.
Because when they talk to each other, then the boots on the ground people believe that they actually are bringing some experience, even though they're sitting far, far away. And the people who are sitting far, far away start to recognize there are other factors, other variables they should be aware of when they're doing their interpretation. And they start to do a better interpretation than simply, like you say, looking at the wall of screens and going, well, that line's a little bit higher than all the other ones. So let's send somebody out to that one, right? They start to go, there might be a reason for it that's simpler than that, right? And get to the root cause faster.
So maybe one last question, which would be, I think condition monitoring, let's say as a discipline, has been pretty broadly adopted by a lot of industries now. Obviously, there are some that are kind of lagging behind. Maybe they don't have the resources, but there's plenty of industries that are using a combination of, VA, thermography, ultrasound, oil analysis, probably even some of the motion amplification tools, electrical signal analysis, all the rest of it. Of the main 4, sort of the core 4 disciplines, I think there's often a tendency to think that one has supremacy over the other, right? So here in Australia, VA is kind of king. You can throw a rock and hit about 10 VA Cat 1s and Cat 2s. And I squarely blame a man called Clyde. I'm going to call him out, Clyde Volpe, because he was such a bloody good trainer. he was the Mobius trainer here for probably 10, 15 years or something, and he was just extraordinary. Universally good feedback on people attending his courses, and so they were extremely well attended, and he has created an army of VA Cat 2s all around Australia, which is, a fantastic thing, and it's real tip of the cap to him. He's kind of recently retired. Now, Clyde's done an amazing job at sort of elevating the standard of VAs across Australia. Now, it does have the knock-on effect where VA is kind of king, and all of the other disciplines are kind of, not poo-pooed. So how do you see, all of them being complementary? And maybe specifically, what are the kind of failure modes that you think oil analysis is really good at picking up, that some of the others may not be able to see?
Yeah, well, I definitely know what you mean about why some gain popularity. Like you say, I have a way of making oil analysis entertaining, and so yes, I have my own army of converts who, usually as a result of people attending my training, if they're already our customer, we see an uptick in their oil analysis, because back to kind of our earlier discussion, if you believe in something, you're more willing to
Mm.
do it, more willing to try it, more willing to stay with it, even if it doesn't seem to be working. Whereas if you don't really have a whole lot of faith, you're pretty much, going to cause it to fail, because you're going to take bad readings or bad samples, and it's never going to work. So yes, the best success is the best of the four. Does bounce around a little bit depending on who you ask, and I certainly wouldn't offer my opinion as to which one I think is the best, because no one would believe somebody who's got nearly 30 years in oil analysis if they said oil analysis was the best. But what I will say is oil analysis is truly the best at wear and contamination. If it's a wear related issue or if it's a contaminant related issue, oil analysis will pick that up on the first sample and guide you along the way to say, hey, this isn't right. In defense, I would say vibration and ultrasonics will pick up imbalances and alignment issues better than oil analysis ever will. Now, as a catch all, I would say that all three of those technologies would catch every one of those problems I just said. It's where they stand out. Oil analysis, like I said, will catch wear first. Vibration and ultrasonics will only tell you it's wearing once the wear has progressed to a point where the signature starts to look a bit funny. But oil analysis will say, hey, on the first sample that's got higher than normal wear, this isn't normal. Similar with contamination. But oil analysis eventually, if you let it run long enough, could tell you that the machine's out of balance or out of alignment, because it would have probably a high amount of wear showing up. But to be confident that that's what's causing the wear would be at such a point that your vibe guy or your ultrasonics guy told you 6 months ago that that was the issue, because it only took one reading to know that. So each technology, each of the four, has a certain type of failure mode that it is better at than the other ones. But most of the four, even thermography, can detect many of the same problems. So that's where I kind of group them together and say, the word you chose is complementary, that some of them have strengths and, of course, weaknesses that are complementary to the other one's weaknesses or strengths, conversely. And so the two that I find the most complementary are actually vibration analysis and oil analysis. And I think they cover the widest gamut of potential failure modes, from over lubrication, under lubrication, contamination, wear, misalignments, all these things, all the common failure modes. And I'm not going to say that ultrasonics won't do it as well, but vibration and oil analysis have a long history together. There's lots of software out there that merges the two data sets in a reasonable way. So it's got the best support in the industry because, back to my earlier comment, people know it works. They have faith in it. Not as many people have developed the same kind of tools for ultrasonics, which is quickly becoming one of my favorite technologies because of its simplicity of use, right? Back to your comment, you had to be trained to do vibration, right? You can't hand somebody a vibration analyzer and say, hey, here you go, right? They barely even know how to operate it, let alone how to interpret it. But ultrasonics, by today's standards of the acoustic emission ultrasonics, it's so simple that just about anybody could pick one up and be able to detect a few things. They're not going to leverage out all the benefits, but you could point it at a bearing, collect a reading, point it at a different bearing, collect a reading, and go, okay, that bearing's worse than this bearing. Or when they come back in a month, go, hey, this one bearing's gotten worse since I last saw it, right? It's very simple to use. And so I'm starting to lean towards ultrasonics as being the better complementary one, simply because it's a lower cost to get into it. It's less training required to do it. And it's a bit easier to see some immediate payback, because ultrasonics can detect things that vibration can't detect, that are a bit unrelated, but like they can detect air leaks, right? Like sometimes right there justifies the purchase price of an ultrasonic detector is just solving a bunch of steam leaks or air leaks within the plant. Acoustic emission ultrasonics is also pretty good at detecting electrical faults. So, in the old days, you would have had to have bought a FLIR camera for that. Nowadays, you're like, oh, what if I'm getting some of the benefits of FLIR in my acoustic emission ultrasonics, which is mimicking a lot of what I can do in vibration? Now you've almost merged three into one, not quite, but you're getting a very introductory course to all three in one simple handheld device. So I'm like, that's quickly becoming, in a lot of industries I'm dealing with now, a go-to tool, just because of, like I said, it's so cheap by comparison, and it's so little training by comparison that people are liking it. And oil analysis is that old standard, like we said in the first question. They're checking a box. So they're like, well, if we got oil analysis and we've got either vibration, which if you're lucky enough to have a Cat 1, Cat 2 on staff, or back to your previous question, if you send it out to a centralized place, it'll do the interpretations for you, but you at least know how to collect the readings. You leverage that with your oil analysis program together, and you've got, I think, a pretty solid gamut. You don't need all four
Mm.
technologies at all sites. Definitely, of course, each one of the four technologies, like I said, has certain areas that reign supreme, and sometimes it would be nice if you had access to a FLIR camera instead of having to send in an oil sample and ask a vibe guy to come do an interpretation for you. But if you had to choose, kind of thing, I would say that the two to choose would be oil analysis, of course, but that's my bias, and either ultrasonics if you're not willing to invest more time and money into it than vibration. But vibration, yes, is very complementary to oil analysis. So it's kind of the top
Yeah.
two: oil analysis, vibration. Very, like I said, the complementary in so much that each one has a strength, each one has a weakness, but it's the other one's weakness and the other one's strength. So
Yeah, that's really interesting. I mean, over the last sort of maybe 6 to 12 months, I think where I've increasingly seen maybe almost like a divergence or a split is for oil lubricated assets, it'd be oil analysis plus VA. For grease lubricated assets, it's grease analysis plus ultrasonics.
yes,
Because often grease lubricate, well, in a lot of cases, grease lubricated assets, if you're re-greasing with an ultrasonic unit, then you're getting that
yeah.
information already. So yeah, it's interesting to see how these are all kind of merging together, and as people get better understandings of the strengths and weaknesses, where everything is kind of finding its niche. But hey, Evan,
I bet you've seen PF curves, and on the PF curve, different curves depending on who produces them, you will see the points near P labeled with oil analysis, vibration, and so on and so forth, but they appear in different orders. And so I was asked by somebody, they said, "What's the correct order?" And I said, "There is no correct order." I said, "Whoever produced it is basing it off a particular type of failure
yeah,
mode." So I said, if they're showing you an eventual wear out failure mode, the PF curve will list oil analysis as its earliest detector, followed by vibration, then ultrasonics, and usually terminating with thermography. I said, but if the failure mode was based off of a misalignment, I said vibration and ultrasonics would be first, thermography would be third, and oil analysis would be fourth. I said, there is no correct order to this because every type of failure is caught by a different technology at different points of its life. And so, that's the thing about the PF curve. There is no perfect PF curve that explains everything in life. It's like, no, it's just a concept to help you understand there's a point P where the potential failure exists. There's a point F where it's going to fail. F happens. You can't change that F's going to happen. Question is, can you find P sooner? And that's by employing the right technology for that particular failure mode, not for that particular asset, for how it's going to fail. And if it fails differently, yeah, the technology you needed to catch it is going to be different each time. And so that comes back to why you should be as complementary as you can and not rely on any one technology. Try and rely on at least two, and if you can, three. And of course, if you really, won the lottery and you could get all four, then you would have the best opportunity to do as much as you could to catch as many of those P's before they progress all the way to the F of the failure curve. So that's just it. There's no one answer.
yeah, that's awesome. And that feels like a really good place to end it. I mean, Evan, hey, really appreciate you coming in to
Yeah,
give us a bit
thank
of
you.
bit of a bit of a history lesson, a bit of a technical lesson, obviously some stories from your experience as well, from your time in the oil analysis field. So yeah, really appreciate the time and thanks for coming on.
Yes, well, thank you for having me.